of our electronics course, and this module is about transient circuits. What do we mean by transient circuits? So far, most of the circuits that you might have studied uh, have been static. There is no time dependence. So you have potential differences, voltages, currents, resistors. Uh, all of these quantities, they don't change with time. Now for the first time, we're going to be looking at circuits in which the current, the voltage, the charge, etc. are actually functions of time. You are already familiar with DC sources versus AC sources. So DC sources produce voltages and currents which are constant, and AC sources produce voltages and currents which are time dependent. So for example, you might have a sinusoidal voltage or a sinusoidal current. So that is one form of uh, time dependent transients in circuits. But that's not the only form. It is also possible to get time dependence with a purely DC source. So we are also going to look at sources like that. So let's look at what are the main elements involved in our study. Three main elements we have. The first one you're already familiar with, resistors. The potential difference across a resistor is always proportional to the current flowing through it. And the constant of proportionality is the resistance, which is measured in ohms. This you have been seeing since your 9th or 10th standard. There's nothing new about this. The next one, the next element that we are interested in is the capacitor. Capacitors, I'm assuming you have also studied capacitors before. Capacitors are a pair of conducting plates which are very close to each other, separated by some dielectric material. And what the capacitor does is it stores charge on it. So the potential difference across the plates of the capacitor, the potential difference is proportional to the charge stored in the capacitor, and the constant of proportionality is 1 over C. C is called the capacitance of the capacitor, which is measured in units called farad. So what is the unit of farad of capacitance? Farad. Farad is just coulomb over volts. The third element that we are going to look at is the inductor. You may or may not have seen this before. Inductors are just current carrying coils. Now you know that if you have a current flowing through a coil, it generates a magnetic field. Now if that current is time dependent, then the magnetic field will also vary with time, and a time varying magnetic field induces its own EMF. This is from Lenz's law. So on an inductor, the potential difference across it is proportional to the rate of change of the current flowing through it, and the constant of proportionality is L, which is the inductance of the inductor, and inductance is measured in units called Henry. So if you look just from this formula, Henry is just voltage second divided by ampere. That is the unit Henry. So these are the elements that we are interested in the course of this module. Let's start looking at some transient circuits. The first transient circuit that we will look at is called a series RC circuit with a DC source. Let's draw the circuit for this, and the circuit diagram for this kind of circuit. So we have a source E. This is a DC voltage source. I'm going to put a switch in this circuit, and I will explain to you later what this switch does. and this is RC. So I'm going to put one R and one C in series. So this is the circuit. Let me explain what the switch does. This is a two-way switch. If I move the switch up, then this voltage source E becomes connected to R and C in series. So when that happens, the capacitor can start charging. Once the capacitor has finished charging, what I will do is I will move this switch to the down position. Now if it's connected to the down position, you can see that the source is no longer in the circuit. It's only R and C in series and nothing else. So now the capacitor can start discharging. So this charging and discharging of the capacitor is what will give the time dependence of this circuit. What is the maximum charge that you can store on this capacitor? So typically Q is C times V, V being the potential difference. Now in this circuit, the maximum potential difference that you can ever achieve is this source voltage E itself. So maximum charge on the capacitor, let's call it Q0, is C times E. Okay. So now let's study. So we'll first study the charging of the circuit, and then we'll study the discharging of the circuit. So first, charging mode. What this means is now the switch is in the up position. Let's write down the equation which describes this circuit in this case. If you apply Kirchhoff's voltage law to the circuit, what that says is that the potential difference E provided by the source has to be equal to the potential difference across the resistance and the potential difference across the capacitor. This is Kirchhoff's voltage law. Now as we have seen, the potential difference across the resistor is just IR, and the potential difference across the capacitor is Q over C. Now I don't want current and charge both, so why don't I write current as rate of change of charge? And now you see, I have a differential equation in Q. And this is a simple linear differential equation. I can solve it very easily, just separation of variables. So let's do that and see what we get. So E minus Q over C is dq over dtr. Yeah. So dq divided by E minus Q over C is dt over r. And this I can integrate because the variables are already separated. I have Q on one side, I have T on the other. So if I integrate this, on the left side I just have a log function. And I must also introduce a constant of proportionality. Let me call it K1. Now how do I evaluate this constant of proportionality? At time t equal to 0, that is when I just moved the switch to the up position, the capacitor had no charge on it. It just started charging at that point. So I will say at t equal to 0, the charge on the capacitor, initial charge is 0. So when I plug that in, I get log of E minus C is, this is 0, so just K1. So plugging that back into this equation, I get log of E minus Q over C divided by E is minus T over RC. And if you do a little bit of arithmetic jugglery with this, you will see that Q equals E over C 1 minus e to the minus t over RC. Now notice, no, E times C. Now you will notice that E times C is just Q0. So what this means is that Q is Q0 1 minus e to the minus t over RC. What does this look like if I try to plot it? What does the time dependence of the charge look like? Let's see. So on the x-axis I plot time, on the y-axis I plot the charge. So suppose this is Q0. Can you see this color? Yes, you can. Then this function, if you plot it, it will look something like this. So as you can see, when t is 0, this exponential part becomes 1 and q becomes 0. But we knew that. In fact, that is one of the boundary conditions that we used to find out the constant k1. So when t is 0, q has to be 0. When t is very large, so if you take t going to infinity, this exponential term becomes almost 0. So you get q equal to q0. So as you go towards infinity, q starts to approach the value q0. And that is what we expect. So if you wait long enough, then the capacitor will get completely charged. Now this quantity RC appears everywhere. RC is called the time constant. And this quantity RC, it controls the rate at which this circuit will charge. So for example, if I take a value of RC that is large, then this corresponds to longer time for charging, or you might call it slow charging. Whereas if I take a smaller value of RC, this corresponds to less charging time or fast charging. Let's look at this graphically. So as a function of time, I'm plotting the charge, and let's mark Q0 over here as we did before. Now let's say for some typical value of RC, suppose the charging as a function of time looks like this. Then if I take a larger value of RC, then the charging will look like this. And if I take a smaller value of RC, then it will look like this. Right? So that's why we say RC controls how fast or how slow the charging process is. Let us now calculate what is the current flowing through the circuit. We have already seen over here what is the charge uh, accumulating in the capacitor. So we just take time derivative of that. That will tell you how much current is flowing through it. So I is dq by dt. First term is q0, that vanishes, so the derivative is minus, but that will go away. So q0 e to the minus t over rc divided by rc. Or if you want, you can write this as e over r. So this is the current that is flowing through it. How about the voltage? What is the voltage, the potential difference across the capacitor, and what is the potential difference across the resistor? So let's find out. Potential difference across the resistor is just current times the resistance, and current we calculated on the previous page. So this is Q0 over RC e to the minus T over RC times R, which is Q0 over C, or e to the minus T over RC. What about the potential difference across the capacitor? This is just the charge on the capacitor divided by the capacitance. So this looks like this: Q0 1 minus T over RC divided by C. Q0 over C is just E. Yeah, let's look at these graphically. Oh, before that, if you notice, if you add up VR and VC, what do you get? These exponential terms cancel off and you're just left with E. And this is nothing but Kirchhoff's voltage law. We started off with this, in fact, and we have verified that we are getting back consistent results. So no matter how the potential difference across the resistor and across the capacitor change, they will always change in tandem in such a way that the sum total of these two will be equal to the uh, the uh, the potential difference, the EMF that the cell was giving you. So if we plot this as a function of t, let's put v over here, and we'll call this E. So what does VR look like? VR at time t equal to 0, it is equal to E, and after that it is exponentially falling. So it will look something like this. VC, on the other hand, looks like this. So one is decreasing, one is increasing, and both are exactly increasing, decreasing in such a way that the sum total is always equal to E. So this concludes our discussion about what happens when you have an RC circuit, RC series circuit, so a circuit in which a resistor and a capacitor are in series with a DC source, and you are charging. So charging is done. Next we are going to see what happens when you are discharging the circuit.